Okay, this is Unit 4, Lesson 1, Inverse Variation and the Reciprocal Function. Our essential question is, how are inverse variation and reciprocal functions related and represented? Okay, here's our table of contents. Identify inverse variation. An inverse variation is a relation between two variables such that as one variable increases, the other decreases proportionally. For the table to represent an inverse variation, the product x and y must be constant. A direct variation is a linear proportional relationship between two variables where one is a constant multiple of the other, usually expressed as y equals k times x. For the table to represent a direct variation, the quotient of x and y must be constant. Does the table of values represent an inverse or direct variation, or neither? So we have x are 1, 2, 3, 4, 6, and 12, and y are 12, 6, 4, 3, 2, and 1. Okay, so the first thing I'm going to do is I'm going to multiply x times y together. So 1 times 12 gives me 12, 2 times 6 gives me 12, 3 times 4 gives me 12, 4 times 3 gives me 12, 6 times 2 gives me 12, and 12 times 1 gives me 12. Okay. Then we can divide y by x, or you can do x by y. You'll get the same result regardless whether it is constant or not constant. Okay, so 12 divided by 1 is 12, 6 divided by 2 is 3, 4 divided by 3 is 4/3, or 1 1/3. 3 divided by 4 is 3/4, 2 divided by 6 simplifies to 1/3, and 1 divided by 12 is 1/12. We can see that x times y is the same. That's our constant. So there is a constant value here. So in this case, it's an inverse variation because x times y is constant number. Okay. How about 4x is 1, 2, 3, 4, 5, and 6, and y is 2, 4, 6, 8, 10, 12. Okay. So x times y, 1 times 2 is 2, 2 times 4 is 8, 3 times 6 is 18, 4 times 8 is 32, 5 times 10 is 50, and 6 times 12 is 72. There's no constant variation here. Okay, so now we can see if it's a direct variation. Y divided by x, 2 divided by 1 is 2, 4 divided by 2 is 2, 6 divided by 3 is 2, 8 divided by 4 is 2, 10 divided by 5 is 2, and 12 divided by 6 is 2. We can see that there is a constant variation here, and this is a direct variation because when I divide y by x, I get the same number every time. How about for x, where x is 1, 2, 3, 4, 5, or 6, and y is 20, 17, 14, 11, 8, and 5. Okay, so if I multiply through, I get 20, 34, 42. I can already tell this is not going to be an inverse variation just because I have two numbers right to be an inverse variation. All the numbers have to be the same when I multiply x times y. Okay, I can figure out if it is a direct variation by doing the division to finding the quotient. So 20 divided by 1 is 20. 17 divided by 2 is 17 halves. I can tell right away it's not a direct variation because of the fact that I don't have a constant with my quotient. Okay. So this is neither an inverse nor a direct variation. Inverse variation. When a relation between x and y is an inverse variation, we say that x varies inversely as y. Inverse variation is modeled by the equation y equals k divided by x, or with an equivalent form, x equals k divided by y, or xy equals k, where k cannot equal 0. The variable k represents the constant of variation, the number that relates the two variables in an inverse variation. Okay, so we can also see this with a triangle. Okay, so you can use a triangle format to do this. Okay, and I split the triangle into 3 sections. Okay. So I can see that x varies inversely as y. Okay. So here's my constant of variation. So x times y is going to give me k, or k divided by x is going to give me y, or k divided by y is going to give me x. All right, notice when x is doubled from 1 to 2 and 4 to 8, the value of y is halved. So 1 to 2, I want 24 to 12. So 24 divided by 2 gives me 12. Same thing with 4 to 8. When I doubled, 4 times 2 gives me 8. So 6 divided by 2 gives me 3. Okay, so you're seeing that when x increases, y is decreasing by the same rate every time. Use inverse variation. In an inverse variation, x equals 10 when y equals 3. Write an equation to represent the inverse variation. Then find the value of y when x equals 6, negative 6. So again, I'm going to use this formula that I found, y equals k divided by x. Okay, again, k is my constant variation. I know my x and I know my y, so I'm going to substitute those values in. And then I'm going to solve for k. And I can do this by multiplying 3 times 10, which is going to give me 30. So my constant of variation is 30 in this case. Okay. I'm going to then use that information to substitute it back into the equation. Okay, so again, y equals k over x. K is 30. And I'm going to substitute x equals negative 6 into my equation. And I'm going to solve for y. 30 divided by negative 6 gives me negative 5. What if x equals 6 and y equals 1/2? And then I need to find the value of y when x equals 15. Okay, so again, I'm going to write that equation, y equals x, k over x, substitute my values for x and y in, and then simplify. So I'm going to multiply 1/2 times 6, which gives me 3. So my inverse variation formula is y equals 3 over x. Okay. Now I'm going to substitute 15 in for x and simplify. I can't just divide. I'm not going to get a whole number. 3 divided by 15 is not a whole number. I'll get a decimal. So I'm just going to simplify it into its simplest form, which in this case is 1/5. Use an inverse variation model. On a guitar, the string length S varies inversely with the frequency F of its vibrations. The frequency of a 26-inch E string is 329.63 cycles per second. What is the frequency when the string length is 13 inches? Okay. So effectively, I've used a capo or a clamp to half this string. Okay. So I'm going to use the same type of thing that I previously used. I'm going to set up the formula. Okay. So in this case, instead of X and Y, I'm going to use S and F because it's the string length and the frequency. Okay. And we said that S varies inversely with F. Okay, so that means F represents my X value and S represents my Y value. I substitute what I know, so the 26 and the 329.63 for S and F respectively. Okay, and then I simplify by multiplying 26 times 329.63. Okay. Now that I've solved for K, I'm going to write the equation for the inverse variation. Okay, which again is just substituting that value for K back into it. And then I want to know what my frequency is when I have a string length of 13 inches. So I'm going to substitute 13 in for S. Okay, and then I'm going to solve. Okay, this is the other point where the triangle actually can come in really handy, right? So if I have this triangle, okay, so right now I'm dividing K by F, but in order to get F by itself, I would just divide K by S. Okay, so I'm going to take 8,570.38 divided by 13, and that's going to give me my value for my frequency, which is 659.26. Okay. You can also double check and make sure that this works by doing the 8,570.38 divided by 659.26, and you'll get 13. Graph the reciprocal function. How do you graph the reciprocal function y equals 1 over x? Okay. So normally we have y equals x, which is just a straight line. It's a linear function. With the reciprocal, it just means that I'm flipping it over. So reciprocal is 1 over whatever I was just talking about. So in this case, x. The reciprocal function maps every non-zero real number to its reciprocal. Okay. So the reciprocal of 2 is 1 over 2, or 1/2. Okay. Consider the domain and range of the function. My domain is all values of x except for x equals 0. X cannot equal 0. If I substitute 0 in for x, I would not get a solution. It's going to be an undefined portion of my graph. Okay. My range is also y, where y is not equal to 0. So again, if I have y equals 0, I can't have, there's nothing I can put in for x to get y equal to 0. It's, again, going to be undefined. If x equals 0, that will result in an undefined expression, so x cannot equal 0. Second thing I want to do is graph a function. So I can either use technology or I can create a table to do this. If I create a table, I just substitute some values in. Again, I can't use 0 because 0 is going to give me an undefined function. And it'll give me a graph that looks something like this. I can observe the graph of y equals 1 over x as it approaches positive infinity and negative infinity. So as I'm getting closer and closer to positive infinity, I'm getting closer and closer. My value is getting closer and closer to that line. It's the same thing if I'm going x towards negative infinity. Okay? I'm getting closer and closer to this line. This line of y equals 0, I will never cross it. I won't ever touch it because if I do that, I would get y equals 0, which is an undefined portion of this graph. So this creates what is called an asymptote. An asymptote is a line of a graph that approaches, is a line that a graph approaches. Asymptotes guide the end behavior of a function. So again, I'm going to get closer and closer to this line, but I will never actually cross this line right here. This line right here, okay, I will never cross it. I'm going to see that I also have a vertical asymptote at this point, which means I will never cross that line either. I'll get really close to it, but I'll never actually touch it or cross it. Okay. So as x approaches infinity, f of x approaches 0. The same is true as x values approach negative infinity. So the line y equals 0 is a horizontal asymptote. Okay. I can observe the graph of y equals 1 over x as x approaches 0 for positive and negative x values. So again, as I'm getting closer and closer to 0, whereas my y values are becoming greater or less than, I can see these values, okay? So as I get closer and closer to 0, so 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, I'm seeing that my y values are increasing exponentially. Okay, so they 1, 10, 100, 1,000, 1,000, 10,000, okay? So as x gets closer to 0, the value of the function gets larger and larger. And you can see this right here. So as I get closer and closer to 0, I'm getting larger and larger. And the same can be seen from the other side for positive values of x as x approaches 0, f of x approaches positive infinity. So I'm going this way, getting larger and larger. You can see this for negative values as well, right? So as I get closer and closer to 0 from this direction on the left side of my graph, I can see that I'm getting greater and larger numbers towards negative infinity. So as x gets closer to 0, the value of the function approaches negative infinity. For negative values of x, as x approaches 0, f of x approaches negative infinity. The domain of the function excludes 0, so it does not include 0. So the graph will never touch the line x equals 0. The line x equals 0 is a vertical asymptote. Graph the translations of the reciprocal function. So I want to graph g of x equals 1 over x minus 3 plus 2. What are the equations of the asymptotes, and what are the domain and range? So here is my parent function. So that's the first thing I want to do is remember my parent function. Okay, I also want to remember that when I add or subtract h to x, it moves the graph horizontally. And in this case, we're moving the graph 3 units to the right. So that minus 3 in the bottom of my denominator, bottom of my fraction in my denominator, tells me I'm moving 3 units to the right. Okay. I also have this plus 2 on the end. Remember that when we're adding or subtracting k, it moves the graph vertically, so up or down. In this case, we're adding 2 to the graph, which means that the graph is going to move up 2 units. So what I'm going to do is I'm going to move these asymptotes, which were originally at x equals 0 and y equals 0, over 3. So my vertical changes from x equals 0 over 3, and then I'm going to go up 2. Okay. So I have new vertical asymptotes at x equals 3 and y equals 2. Okay, so it's a vertical asymptote shifted 3 units to the right. Horizontal is shifted 2 units up. The line x equals 3 is my vertical asymptote. The line y equals 2 is my horizontal asymptote. Okay, my domain is x, where x cannot equal 3. Again, if I put 3 in, that's going to give me a denominator of 0, and I can't have 0 in the denominator of a fraction. My range is y such that y cannot equal 2. Again, I will not be able to touch that y equals 2 line. Okay. Summary. Okay. So in conclusion, an inverse variation means that the product of x and y are constant. A direct variation means the quotient of x and y are constant. Okay. For reciprocal functions, I can use this formula, this y equals a over x minus h plus k. A, again, is my stretch or compression. H is my horizontal translation, and K is my vertical translation. And that is the end of Unit 4, Lesson 1.